So we have two homeworks last week. One is defining research questions, and the other one is PCA analysis. So Jay, please explain your research idea and with an example.
Change my research question.
That's fine.
Yeah, so the topic is that, and actually I found my data, so I want to save the exchange rate from 2005 to yesterday, but I don't know, but I think this is a systematic problem to save the data, so I can't make that.
Okay, how about your PCA homework?
PCM.
Okay. Why don't you come forward and run your program?
Actually, okay. I want to go to my reference site.
Okay, I just download your program and run it. That's all I want.
Okay.
If you want to go to Google Groups webpage,
Okay.
just a moment. It is already open. Yes.
At first, I deleting
Download your program.
Download.
and run.
this. Okay. How can I download it? Just copy and paste.
Yes. Whatever you want.
Okay, at first I deleting column A because I don't know. After call my data, and I wanted to calculate the covariance of this data. However, I failed to this, so after deleting column A, I can make it a dual. So I defined A is data column 1 to 8 and make a calculate covariance like this. So these are the data, so these columns covariance, and after that use this I write the PCA order PR comp and and calculate standard deviations of these data like this, and this order shows standard deviation and rotations about main principle, right?
What is rotation?
Actually, I followed my reference sites, so.
There is a factor loading.
Huh?
There is factor loading.
Factor.
Same here. Do you remember what is factor loading? Anyway, we will see.
Okay. Then after calculated these data, just write this order on to the R, and it shows standard deviation and proportional variance, so I can know about what is the main principles and make a graph after writing this order. Then actually I don't understand this order, why I should this. Then so many data. Then this order makes the PDF file and shows the graph of this PCA. I don't know why it is. Ooh. I don't know how can I fix it to open this file. So,
Did it work when you
yeah,
did it at home?
yeah. The file is there, my laptop.
So there is a graph for the first physical component.
Yeah.
Are you sure? Plot to PDF. Okay, plot to PDF family. Korea 1 DEV. Okay, P1. Just a moment. Okay. You know what? The file size is 0.
Yeah. So after make the order like this.
Yes. Off. Right. And let's try it again. Okay. Okay. So anyway, you will save this plot here, right? So therefore, what we can do is by plot directly here. Ah. Okay, is this what you want?
Yeah.
This is not a graph for the first principal component. It is a graph, it is a plot of your entire data expressed in terms of two axes, PCA1 axis and P second principal component. So these two lines are basically generated by vector loading. Okay, vector loading, and you plot your data into two axes, PC1 and PC2, to the direction of two vector loadings. So this is not what I want. What I want is time series plot
Time series.
of first principal component. Okay, go to your place. Anyone wanna challenge? Any volunteer?
I use Spring Code and PR Code both, but I want to know what is the difference.
I don't know exact difference between them. Yeah. Actually, okay, I'll show you my code. Yeah. I also tried both of them, and they generate slightly different answer. Actually, not slightly, they have seriously different answer. And I don't know what kind of routine method they use. Anyway, set. And my code, this is my data. Let's check it. Okay. Yes. And this is my code. So, source. So last week I did work with Princom, and the output was different from what I thought. So I tried different syntax for principal component, different function, different command for principal component analysis, and I found more stable routine, which is PRCOM. Okay? So actually I suggest you to use PRCOM from now. Anyway, I tried both of them, and to show you my code. So actually I did principal component with three different methods. TRCOM, PRINCOM, and I did it from the scratch using the eigenvalue decomposition. So okay, my data is read. Can you read it? Here, can you read the font? Use these fonts. Are they too small or fine? Can you read them? It's fine. Okay, first, my data. Anyway, let's. No. Okay, 12. Okay, my data is, of course, I read data from 2 to 9th column. This is all you know. And I did PCA analysis with PRCOM. Okay, this is PRCOM. And I did another PCA with PRINCOM like this. Okay, in both cases, I scaled the data. And in this case, my input is correlation matrix. So basically, they should generate the same answer. So variable means set to 0, blah, blah, blah. So SD is my data PCA. So in the previous PRCOM, I saved standard deviation into SD, into variable SD. Okay. So SD looks like this, and my data PCA looks like this, and my data to PCA2 looks like this. Okay, standard deviation and blah blah blah. Okay. So as you can see, the eigenvalue is slightly, oh, they are same now. PCA2. Scores. Okay, and then standard deviations. Okay. C by okay, so answer is almost same. Okay. So component 1, 2, 3, 4, 5, 6, 7, they are same. So they are standard deviations of each principal component. Therefore, if we square this, basically they are eigenvalues, right? Do you remember? So basically eigenvalues of a correlation matrix is basically variance of each principal component extracted from that correlation matrix. So loadings are basically loadings are why I cannot move. Okay, loading, they are the eigenvectors. Okay, so loadings 2. Loadings 2. So if we compare these two eigenvectors, now they are slightly different, and this output looks actually cleaner. So that's, I think the PRCOM routine is, I think, better. So when you extract factor loadings, which are eigenvectors of the matrix, if we use PRCOM, you have to use rotation. If you use PRINCOM, you have to use loading. This syntax is more intuitive, but this one seems more stable. And then, okay, I define row names into this column name. So basically what I did is, it is like 1, 2, 3, 4, 5 before I do this. So I name each row following the column name of my data. So therefore now I can see more easily how each of my original data is related with my principal component. Okay, so basically first principal component is this multiplied by this, and this multiplied by something like that. Okay, and of course we have to multiply the eigenvalue, which is the variance of the original matrix. Okay. And the score matrix, to get the score matrix, so score matrix is something I want. So score matrix, okay. C bind scores 2. This 2. Yeah, still it is too large. Anyway, yeah. So this part is, so they are the score matrix, so which is basically, they are the principal component. They are the factor loadings multiplied by eigenvalues multiplied by original data. Okay. So what I want you to do was Okay, scores 1 is basically this is your first principal component, and basically what I wanted you to do was plot this one and do the plotting. Something looks something like this. So they are basically first principal component of the original data. Since my original data, the original variable were proxy for investor sentiment, therefore is standing for investor sentiment. I think the better graph is type line. Okay, so this is basically investor sentiment. Okay, any question? So it was your homework. This is the routine that I use the pre-installed principal component function like prcom and printcom, but instead I can start from the eigenvalue decomposition from the scratch. So first I have to calculate variance, covariance, correlation matrix of my original data, which I save as R. Okay, R. So R looks like this. So it is a correlation matrix, correlation between this and this. Okay, so it is correlation matrix. Okay, yeah, it is correlation matrix. And then here I did eigenvalue decomposition. Okay, using the data, using the correlation matrix. So let's type my EIG, my eigen analysis. So this is my eigenvalues. Okay, this is my eigenvalues. So it should be, so each eigenvalue is again, each eigenvalue is the variance of each principal component. So in the previous output, the where is it? This one, it is square of this item. Okay, I will compare that shortly. And then yes, so actually what I can do is basically this one. So this one is basically my I dot values generate of okay. So basically my I dollar values gives me the eigenvalues of the matrix, and they are the so if I do the square root of this one, then it should be the standard deviation of each principal component, right? So therefore, I can now compare those three. So eigen 0 is looks like this, and eigenvalue 1 is diagonal term of the my score matrix, and eigen 2 is diagonal matrix of my second score matrix, which is computed with printcom. Okay, so it looks like this. So I can compare them. C bind. So it's column bind, basically column bind. Eigen 0, eigen 1, and eigen 2. Okay. Then I have answers like this. So originally, I mean, if they generate only exact numbers, the three numbers should be same. But as you can see, they are kind of slightly different from each other. Slightly different from each other. And then I can calculate single values from eigenvectors. So the eigenvectors are factor loadings, right? So I can compare factor loadings of each other. So this loadings long is basically yes. Actually, let's use this command. My eigenvalue vectors and their factor loading. So basically, they should be same to loadings and loadings too. Okay, they should be same. So this one should be same to this one, and this one should be same to this one. Actually, yeah. Okay, and then let's add a name. Loadings long. Column names my data. Column names my okay. Column names of my data. Okay, if I do this, then loadings long. Yes, and I have names. So they should all generate same answer, but they are slightly again different from each other. Okay. And then to compare the answers of each other, okay, I can compare. So this SD is the standard deviation from principal component from the routine PRCOM, right? And SD long is the square root of vehicle eigenvalue. So if they use exactly same method, if they all generate exact answers, the difference between eigenvalues should be 0. But in reality, actually it is close to 0, so there is no problem. And the factor loadings, but this first loadings is again the factor loadings generated from PRCOM, and the loadings long, it is factor loadings generated from the longer process using eigenvalue decomposition. So if we compare these two, if we subtract this one from this one, the answer should be 0. But in reality, the range is from the minimum of the difference is about -136, and maximum of the difference between the elements is actually 1.86. So actually there is a significant error between the two routines. Okay, and even score matrix. Okay, even score matrix. Square matrix, we have even larger numerical error. So if they all use exact procedure, the answer should be same, but somehow they all generate slightly different numbers. Okay, eigenvalues. Yes. And actually, this is another way I did it. So calculating singular values from the eigenvalues. So this is my eigenvectors, loadings long eigenvectors, and I give the name. And I can define a function, standardizing function, which is basically I subtract mean and divide with standard deviation x. Then basically what I did, I standardized x such that x is distributed as standard normal, right? And then I apply for given data x. So for data x, my data, okay, I apply this standardization function and I save that as x. And the score matrix basically, as I explained, score matrix is basically my eigenvectors. This is multiplication of eigenvector and my original data, right? So again, alternatively speaking, my score matrix is basically, score values are basically my normalized original data and multiplied by factor loadings. Okay, so factor loading is the coefficient for each my data. And in this way, I can calculate scores and I can calculate diagonal terms of basically variance of this score matrix, and again, these eigenvalues, which should be eigenvalues and which should be also generate same answer. But in reality, let's check. In reality, they are slightly different from each other. Okay, especially for small score, small principal component, weak principal component, and for small eigenvalues. Anyway, I think this hyperbole, it explicitly shows the relationship between principal component analysis and then singular value decomposition. Any question about principal component analysis? Do you think you can do principal component analysis with any data?
Can I see the result of score 1 and 2? I mean, one is with pre-comma, one is pure comma.
Beg your pardon?
So I just want to the plot. The
Oh, plus, compared to
result.
plus.
Yes, I want to compare the score and score 1.
Oh, okay.
Also the result is
Okay, so again, let's see bind. Okay, so scores first element, it is generated from PRCOM. And scores 2, this is generated from PRINCOM. Okay, and they are yes, they are. Anyway, it is slightly different, but yes. Anyway, they look similar to each other. Okay. And then let's plot the second part of plot scores 2, 1, type L, type line. This looks similar to the previous graph. For my curiosity, let's plot the second principal component. Second principal component looks like this. What does that mean? Copy this. Okay. So it is. Okay. Anyway. Any other question? So again, eventually what we usually need is to generate the score matrix. And it is very easy to generate score matrix once you know how to do the eigenvalue decomposition. Principal component is simply first you normalize the data. Okay. Okay. This is the so what you can do is first you normalize the data, and once you normalize the data, then you multiply. Okay. So for principal component, first principal component, what you have to do is first you find the biggest eigenvalue, and for that biggest eigenvalue you find the eigenvector, corresponding eigenvector, and the eigenvector will become the coefficient for each column of your original data. So what you have to do is simply multiply, okay, each data with each element of the first eigenvector and sum them up and normalize it basically. Then you will get the first principal component. That's pretty easy. And for second principal component, what you have to do is to find the second eigenvalue and then corresponding eigenvector, and again multiply each element of second eigenvector with the data, each column of the data. Then you will get the second principal component. Any question? That's pretty easy, right? No question. Okay. If you want to know more about principal components, basically you have to study eigenvalue decomposition. So, any book about linear algebra will explain in very detail about eigenvalue and eigenvectors. And today, let's go to the next topic. Now regression. Okay. Actually, let's define our homework. Let's determine our homework first for next week. Okay. Next week homework is actually I want you to do regression analysis of using Kenneth R. French's data. Okay. What you have to do is first go to Kenneth R. French data. Okay. And in his data, you can download pharma French factors. What is it? No. Okay. So it is pharma French factors. So there is 3 pharma French factors. Okay. So they are market factor. It is also also called market premium. So it is return from market portfolio minus risk-free rate. And SMP is the basically difference of the excess return of the small stock over large stock. HML is basically excess return of value stock over growth stock. Did you learn this basically? Did you learn pharma French 3 factors in other class? No. Did you take investment class? Yes, but you didn't learn that. Okay, so you all know capital asset pricing model, right? So basically, capital asset pricing model says, Hyun-jung, what is capital asset pricing model? What is it? What is it? You can remember? Here, what is capital asset pricing model? You learned that, right? You learned, but you forgot. Okay, do you remember? What is capital asset pricing model?
I remember I run that, but it's pretty hard to explain what is kind of.
No, it is not hard to explain. It is just one equation, okay? Right? This is capital asset pricing model. Here, now does it look familiar? Okay. So actually we can get rid of this expectation sign. Okay. Or something, right? The capital asset pricing model says that. So this is risk-free rate, and this is return from an arbitrary asset, on asset traded in the market, on asset I. And this part RM is return from your market portfolio. Again, RF is your risk-free rate, and epsilon is some error. So in capital asset pricing model says that we can decompose. First, it says many things. First, it says that we can decompose an excess return of an asset into 2 parts: systematic part and idiosyncratic part. Okay, systematic. You know what? Capital asset pricing model is enormously important. Idiosyncratic part. So basically, you can get rid of this part by holding a lot of assets, right? But this part you cannot get rid of, because for all assets, whatever I you have, you all have this part. So any times beta is greater than 1, okay, how many assets you have, basically you cannot get rid of this part because it affects everything. So capital asset pricing model says first you can decompose excess return of asset to systematic and idiosyncratic part. And then second, capital asset pricing model says that the systematic part is simply beta multiplied by market premium. Premium of the excess return market over risk-free rate. So basically it is single factor model. It has only one factor. Okay? One factor. Okay? It has one systematic factor. Okay? So this implies that, okay, this expected return. So if you believe capital asset pricing model, expected return of any asset, expected return of any asset is entirely driven by this thing, right? Because every asset has exactly the same part, this part, right? It is simply excess market premium, right? So for every asset, this part is same. This only different part is this part. So differences of individual asset is entirely explained by only this part. Okay, so capital asset price means that the higher beta is, the higher expected return, right? If Naver generate higher expected return than Samsung Electronics, it means that maybe Naver has higher beta than the betas of Samsung Electronics. So it means that since all the excess return of an asset is explained by beta, basically we can draw this one. This, let's say x-axis is beta, y is the excess return, RF, something like that. Okay? So basically in the market, okay, in equilibrium, all assets would be look like this. Okay. So if we believe capital asset price model, excess return is basically linear function of the beta. Okay? So let's say it is 0, then what should be this point? Oh, sorry. Okay. Your expected asset return, your expectation of how much Naver will generate until next year, how much POSCO will generate until next year, how much Google will generate until next year, which is your expected return, is entirely driven by, okay, beta, okay. And then if we believe capital asset price model, it should be linear relationship. Okay, given this linear relationship, what is the value of this point? This is free rate, right? You can plug beta equals 0. This part is 0. This entire part is 0. The expectation of risk-free rate is simply risk-free rate. So this is RF. Okay. And what is the slope of this? What is the slope of this graph? This line? What is the slope of beta? Beta? No. Beta is, beta is this x-axis. X-axis is beta. Okay, so it is a relation. Beta is called the regression coefficient, but it is different chart. Okay. What I want to show that excess return is just linear function of beta and entirely driven by beta. And what is the slope? Slope is simply market premium, right? Slope is, so if it is 1, this slope is, right? The slope is market premium. So this is what capital asset price model says. Okay. So sometimes people get confused. Actually, Byung-Chul was just confused. So when we say slope between beta and excess return, okay, the slope is market premium. Okay. But when we actually estimate capital asset pricing model, basically we regress excess return on market return, right? And then beta is the slope of that regression. So when we actually compute estimate capital asset pricing model, we usually use this data. So this is market return, and this is usually excess return, and we have a lot of data, something like this. And when you estimate capital asset pricing model, regression coefficient looks like this. Okay, looks like this, and the slope of this curve is actually beta I. Okay, the slope. So this point is generated by each time. So it is like a cross-sectional graph. It is time series data. It is a snapshot of a given moment. It is snapshot over time. So it is over time. Yesterday, pair between asset I and market return, and today after tomorrow, next year, something like that. They are different. So homework, in your homework, what you have to do is this one. Estimate better. So in the financegoogle.com, okay? In the financegoogle.com, okay? Let's go financegoogle.com. In the financegoogle.com, you can download asset return. So is this, let's take IBM data. So you can get the historical prices IBM. So you can basically calculate return of the IBM over time, right? And then you have this market premium, right? So you regress excess return, and you have also risk-free rate. So what you have to do is first, given the prices, you calculate return of the IBM or whatever you want, and subtract risk-free rate from the return and run the regression, okay, between that excess return over this market premium. That's the homework number 1. Estimating capital asset pricing model. Homework number 2 is multi-factor model. So this is capital asset pricing model, but actually Pharma French famously expanded this model. So capital asset pricing model has just one factor, and the Pharma French model said we have another one. So it is a beta I1 R small minus R large. This is the second factor, and third factor is beta I2 E R value minus R growth. So it is basically a portfolio of small stock. Return from the portfolio of small stock. And this is return from the portfolio of large stock. And this is return from the portfolio of value stock, return from portfolio of growth stock. And return, basically value stock is stock with high book to market ratio. Okay? And growth fund is portfolio with low book to market ratio. Okay? So it is open set with high to low, high minus low. So if you go to Kenneth French's vector, so it's basically SMB is small minus b. Right? Small minus b. And HML is high minus low. Okay? High book to market ratio minus low book to market ratio. So homework number 2 is download stock data. And of course you have to align the date. Okay? Align the date. And regress excess return of an asset over this 1, 2, 3. Any question? Then the question is, okay, how can I do regression with R? Okay, that would be your next question. Oops. And that's very easy. You can search Google. Okay, regression R. Well, I keep neighbor. I hate neighbor. Okay. Okay. I hate. Okay. Okay. So R regression Okay. Then there is a practical regression and ANOVA using R. Okay. Regression using R. There are a lot of resources. Multiple regression. Let's check this one. Yes, regression. So basically it is regression of y on x1, x2, x3. So in your case, if this actually Farmer-French three-factor estimation of Farmer-French three-factor model. So y is excess return of IBM or GE or whatever. x1 should be this one, x2 is this one, x3 is this one. So okay, very easy, right? Just one line, and summary will give you the result. Easy, right? And the command is basically this one. So you can alternatively help and type LM, linear model, LM. Then it will again show you the syntax, explanation about the syntax of regression. Description, LM is used to fit linear models. It can be used to carry out regression. Single stratum analysis, regression, okay? So here is syntax. Good? Any question?
Could you explain what HTML is?
HTML is high is excess return. So high minus low. High means high book to market ratio. Low is low book to market ratio. So when you say book to market ratio, it is like book value of asset over book market value of an asset. So for bond, so asset is, if you believe accounting identity, asset is basically also same to liabilities and then equity, right? So book value of liability and market value of liabilities is very similar to each other often, but book value of equity and market value of equity is often very different. Market value of equity, you can go to accounting report, you can find it. Market value of equity is number of shares outstanding multiplied by share price today. Okay. So anyway, high HML is high book to market ratio forms minus low book to market ratio forms in terms of excess return. Okay. So excess return of the portfolio composed of high book to market ratio minus portfolio return from the low book to market ratio. Any question? So often some people say that the inverse of book to market ratio, M over B, is sometimes called Tobin's cube. M over B is Tobin's cube. You all know Tobin's cube, right? No? Tobin's cube is also very important, but I don't have time to explain that. So please search Google as well. And if you are more interested in Farmer-French three factors, so Farmer-French three factors, okay? Then again, okay, there is Wikipedia, okay? Farmer-French three factor model like this, okay? So exactly same definition of mine, okay? It is the Farmer-French three factor model without expectations, okay? Without expectation. I can get rid of expectation and move RF this part, okay? And since we don't have expectation anymore, I have to add error. Then it is Farmer-French effect model, okay? In academia, for your information, in academia, actually we use 4-factor model, not 3-factor model. In addition to the Farmer-French 3-factor, so it is capital asset pricing model, only this one. Farmer-French 3-factor, this one, this one. And in reality, in many academic research, we use 4-factor, and additional factor is using momentum factor. Excess return of winning stock over losing stocks. And actually, in Kenneth French's webpage, I think you can even download momentum factors. Yes, momentum factor. You can even download the momentum factor. Okay. Any other question? So Sohae is asked today, so please explain the homework and these things to Sohae, okay? Please help her. Is he gonna drop this course? Is she gonna drop the course?
I don't.
No? So, no more question, right? No question about factor models and no questions about homework. Okay, now let's briefly go over what I mean by a regression model. Okay, close, 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 and regression. What is regression? Okay. If I click regression, then we can go Stevenson's web page. He's famous labor economist, very famous, and he has wonderful resources for econometrics. And I will go to his undergraduate course web page. Okay, and univariate regression. Okay. Download his lecture note. Okay. So three of you three already learned econometrics, right? At least statistics. And in this, no, you didn't know statistics. 경영 통계 whatever.
Yeah, I learned that.
Yeah, you learned that, so you know regression, right? Briefly, at least.
What is regression in Korean?
Pegging results. So you learned that, right? Okay. And in the first class, I explained the geometry of regression. But anyway, let's go over this again. It's so slow. Univariate regression. Univariate regression means regression with only one variable. Okay. Besides constant. So basically, estimation of a capital asset pricing model is univariate regression. Estimation of a Farmer-Francis three-factor model is multivariate regression. Okay. Univariate assumption in the let's blow up. Okay. Okay. Let's say y is dependent variable and y is distributed with some. It has some distribution. Such that f is cumulative distribution function. Okay, so we specify distribution of y in terms of cumulative distribution function f. What is cumulative distribution function, by the way? Do you know? 전혀. It's cumulative distribution function. 누적 확률 분포함수. Okay, what is that? Okay, so suppose f is cumulative distributive function. So what x means? When f is cumulative distributive function, what is fx? Do you remember? No. J. What is fx? What is fx? What is fx?
Probability function.
Yeah, it's probability that event, the realization of random variable is smaller than x. Okay? Its probability of epsilon is less than x. So epsilon, when epsilon is distributed with x. Okay? So suppose we have normal distribution. So and suppose this is x, and fx is basically the size of this area. So given the probability density function, the CDF, cumulative distribution function CDF, would be look like this. Okay. So anyway, f is the CDF, cumulative distribution function. And suppose expected value of y is mu I, and variance of y is sigma y. Okay. And it is not necessarily normal. Right. In this case, I don't say f is standard normal, cumulative distribution function of the normal distribution. It can be any function, but at least it should have mean and variance. Some distribution has don't means or don't have variance, like a t distribution. Right? T distribution doesn't have mean, therefore doesn't have variance either. Okay. So anyway, it's not T is something like T distribution. It at least has first and second mode, mean and variance. And then assume that this part, this expected value of y, we can express it like this. Beta multiplied by xi. So expected value can be expressed by something else, some other distribution, some other values, xi. The xi is called the independent variables, y is called dependent variable. So it is like if it is a capital S price model, in capital S price model, yi is basically excess return of a asset. In capital S price model, xi is the excess return of the market, right? So therefore, if we combine them all, basically it means yi equals beta xi plus ui, and expected value of ui is 0, therefore, and variance of ui is sigma square, and then it is very important, xi multiplied by ui is 0. So example, so capital S price model is a great example. Another example is school performance as a function of SAT score. So in this case, y is school performance, x is SAT score. Consumption as a function of income, right? Y is consumption, x is maybe transitory income or permanent income, right? If you want to test Keynesian consumption theory, the income is transitory income. Income someone makes today. If you want to test Friedman type monetary economist or argument, the income is permanent income. And moderate as a function of crime program. So competing. Okay. Now how to fit the curve. Okay. So our goal is to find the balance. Right? Our goal is to find this one. Okay. In capitalist price model, our goal is to find the balance. So basically we have a data. Right? So this is x, I, this is y, I. Right? If it is capital as a price model, it is distribute xi and market return, and then individual asset return over time, something like that. If it is a school performance and SAT score, it is SAT score and the school performance. 학력고사 점수, it is a 한양대 몇 명 간다, 학교별로, something like that. So we have data like this. Suppose we have data like this. And our goal is to find a line that fit this line. Okay? Actually, to find a line that fit that point, the data. Right? And there are actually many ways to fit the line. First one, the most obvious one is to find the distance between the two, right? And minimize this one. minimize some absolute value of some of this one. Another one is actually to measure distance in this way, orthogonal parallel to the y-axis. So this way, possibly. This way. There is another possibility. And the method we are going to use today for linear regression is basically, suppose this is the distance, d4, something like that. Linear regression means to find the line, then minimize this one. T. Okay. So fitting in regression means not like this, but find the distance, this one, and square the distance and add them all and minimize that. The line should minimize this one. That's the regression. We call fitting, so option for fitting, piecewise, okay? Piecewise fitting is something like this. Piecewise is something like this. Find the function something like this, but this is not what we want. Okay? In more advanced econometrics, actually sometimes we do this. Non-parametric is called non-parametric estimation. Or mean squared deviation, absolute deviation. Mean orthogonal squared deviation. Mean orthogonal squared deviation is this way. And what we want is B, mean squared deviation. Mean squared deviations. Okay? And we want to minimize through regression analysis. We want to minimize mean squared deviation of data point from a line. Question? No. Now, estimation, okay? So this is our model, right? This is our model. yi equals alpha I plus beta xi ui. So this is our model. And basically, our goal is to find alpha and beta that fit the data most best, right? So our goal is to minimize mean squared error, right? So basically, in each point of the line is y alpha plus beta xi, and data is yi. Therefore, yi minus alpha minus beta xi square is mean squared error. And we want to sum them up, and we want to minimize sum of mean squared error. And we want to find the line. Line can be completely characterized with alpha and beta. So basically, our goal is to find alpha and beta, minimize this term. The argument minimization is basically this outcome is the solution that alpha and beta can minimize this term. Okay, this is called argument. So argument of mean standard mean squared error. Okay. Find argument alpha beta that minimize sum of mean squared error. Okay. So our goal is to find alpha and beta that minimize this one, and that is extremely easy, right? Through computer minimization, minimized value, all you have to do is get the first order condition. Okay, take derivatives. Okay, do the differentiation and find the solution. Okay, now you all know differentiation, right? So we have this function, this one, and we can take derivative of this one with respect to alpha. Okay, if we take derivative with respect to alpha of this one, then we have this equation. Okay. If we take derivative of that equation with respect of the beta, then we have this. Okay? And then we have two equations, we have two unknowns, so we can solve this. Okay? We have two equations, we have two unknown alpha and beta, so we can solve this. Any question? So actually let us solve this. This is not difficult to solve. So from this equation, so actually we can get rid of 2. Right? We can get rid of 2. And from this equation, basically, alpha means, right? We can subtract alpha outside, right? Then we have alpha n, right? So therefore, alpha is 1 over n and this term. For some given beta, right? For the solution beta, right? So this looks like this, and we can separate these two things, right? So this part and this part, and this part is, by the way, it is average of the y, and this part is average of the x, right? Therefore, this alpha hat, our solution is simply average of the y minus some solution beta minus average of the x, right? Of course, we have to move this, but at least we now know the relationship between alpha and beta solution, right? Okay, so given this relationship, let's go to second equation. So we can get rid of 2, so we have this equation. And for this equation, now we know what is alpha hat. So plug this to alpha hat, okay? This to alpha hat, and this equation looks like this. So what? So if we take a look at this one, it is deviation of y from the average, deviation of x from average. Alright. It looks like this. Right? Looks like this. And again, you can separate from this part, and it looks like this. Right? And notice that, okay, it should be look like this. Okay, and therefore, eventually, beta it looks like this. So beta is basically, this is the, so x tilde is difference between xi minus x bar, okay? Right. So basically, if we divide numerator and denominator with n, basically this denominator, item denominator is basically covariance. Item in the numerator, numerator is covariance. Item in the denominator is variance. So it means that regression coefficient is basically ratio between covariance and variance. Right? So if we use CAPM example again, the beta of capital asset pricing model is a ratio between covariance of individual asset and market portfolio and the variance of the market portfolio. Okay. Maybe I was too fast. So again, let's go one by one, line by line. Okay. Okay. So this is clear up until here. So this hat, this tilde is basically difference from mean, okay, it is deviation. So xi multiplied by x tilde, we can write it down as like this, right? Xi is xi tilde plus x bar, mean of x, average of x, by the definition of x tilde, right? So we have equation looks like this. Okay. And then this is simply sum of this one, and we have this one, right? With this one, but actually this term is a constant, right? So we can put this one here. So we here. So basically this one is tilde square plus average of x and sum of this one. But actually, again, by the definition of this one, this is the same to this one, right? And then if we take a look at this item, it is xi, sum of xi minus x bar, right? So therefore, basically this item, this term is exactly the same to this one, right? Remember? This is average, right? So if we more intuitively, if we put this one outside, it is n x bar, right? And this one, why? Since x bar is average, so sum of individual item is number of data multiplied by average. So this term is the same to this one. So actually this term is 0. So if you multiply tilde and the original data, it becomes the square of the tilde. Okay. So basically this item, okay, so this term becomes xi tilde square, right? And if you do the same operation about this part, it's x same to xi tilde and xyi right? Therefore, yeah, we can transform this one like this, okay? So whenever we don't have tilde, we can put tilde over here, okay? Because it's same, right? Same. Therefore, we have this item, so we can solve for beta. And once we get a beta is, which is simply ratio between covariance and variance. Once we calculate beta, then we can plug this beta into the equation 4, and we can get alpha. Therefore, we can get alpha and beta. Any question? And in addition to that, okay. In addition to that, okay, since we have this is our original equation, and then if we can get the average of each side, we have a relationship something like this, right? And this is exactly looks like this. So we have this, and subtract this from this, then we have this relationship, right? So yi minus y bar is yi tilde. And alpha is the same, so cancels out, and beta xi minus x bar, so x tilde, and this is u tilde, right? And then here it is straightforward that this is equal to 0, okay? And then variance, okay, standard deviation of this item should look like this, okay? Therefore, okay, this equation called linear regression actually, right? Any question? Okay, maybe it is better to derive this equation by hand. So first, UI tilde. So UI tilde is by definition UI minus U bar. Okay. So expected value of UI tilde is expected value of UI minus expected value of U bar, right? And by the definition in the original setup, this is 0, right? And this U bar is simply expected value of sum of 1 over n, right? Because this is average. And you can put expectation here, so 0 minus expectation of UI divided by n and sum. But this is all 0, right? So this is 0. Okay, and about second item, variance of UI tilde. Variance of UI minus U bar. U bar. So it's basically variance of UI minus variance of U bar. Okay. And variance of UI is by our assumption is sigma U square. And variance of this one is variance of basically sum of UI divided by n. Right? But we can put this n outside. So it is a sigma square minus n square over variance of sum of UI. Right? And since this each UI is identically independently distributed, it was our original assumption. Since they are independent, so we can put variance inside. Right? The UI are all independent. Right? Then x and y are independent. So it is sigma square minus n square over 1 sum of variance of UI. But variance of UI is all sigma square. So it is all sigma square, so it is n sigma square. So this cancels out. So 1 minus 1 over n sigma square. So we have this one. Okay. Wait. Square fields. I think it is not n squared, it's just n. Okay? The square term is wrong. So it is 1 over 1 minus n. So you have to. There is no square. So one interesting fact is that, okay, when we have a large number of n, right, we have a large number of data, this term basically, this term converts to 1, right? This, when we have a large number of data, we have a large n, basically this term converts to 1, right? Therefore, given large data, given very large number of data, the variance of this error term of our regression, okay, error term of our regression, indeed converges to the true variance of the error term. True variance of the error term, which we assumed first, right? We assumed first, right? We didn't know this part, but eventually, in the beginning, we didn't know this one, but eventually, our estimate will convert this to that number. Where is it? Yes, convert it to that number. Any question? So, there are two ways to do your homework for capital asset pricing model. First one is, of course, you can use built-in function in R, LM. Alternatively, you can start from scratch and get the beta. You can start from scratch and actually you can use formula over here, right? So when you calculate beta, what you can do instead of R command is to get a beta. First, you can calculate variance and covariance in the given data matrix, right? So calculate covariance and variance and get the ratio and say that as a beta. And once you have obtained the beta, then you plug the beta into this equation and give it out. And if you believe capital asset pricing model is right, alpha should be close to 0. In other words, because alpha is basically plus where is capital asset pricing model plus some constant, and that constant should be 0 if capital asset pricing model is right. Analyze beta. So to analyze beta, okay, beta looks like this. So again, if we divide numerator and denominator with n, right? Nominator is covariance, denominator is variance. So, given the definition of xi tilde is beta, xi tilde plus ui, right? So, actually, yi tilde looks like this. By plugging this relationship over here, again, and can separate out, and we have this part and this part, and this cancels out. This is 1, and we have this part. And this part. Therefore, okay, if we take expectation each side, then expectation of beta head, estimation of beta, basically it is random value as well. Expected value of beta and expectation of beta, which is something we don't know. It is true beta, right? Something we don't know yet. Expected beta, but anyway, it is constant, so it is go outside. Then we have this part, but we can put expectation over here. So this is 0, so this is 0. So this means that our OLS estimate of beta hat is expectation of beta hat is a true beta, right? Beta is something we want to get. So it means that our estimate beta hat is unbiased estimator of the beta, true parameter. Okay. Again. Okay. Beta hat is the expected value of the beta hat. So our OLS estimate is the unbiased estimate of beta. And next, we can compute the variance of the beta. Variance of beta is of course looks like this. And since beta hat is unbiased estimate of the beta, this term is simply this. Okay. Therefore, using equation 7, okay, beta hat minus beta is by equation 7. Okay. Equation 7 looks like this, okay, this part. So beta hat minus beta is simply this one. And then square of this one is simply I equals 1 to n, j equals 1 to n, and cross product of each other. Right? Looks like this. And then since it's a cross product, you can put E inside of this one. Since xi is all data, okay, xi tilde is all data, so we can put E inside. Okay, inside. And since they are all ui, uj are all independent of each other, okay, we will have only this part. And since we already know what is the value of ui, so basically this is the variance of ui tilde, and we know variance of ui tilde is 1 over looks like this, basically looks like this. And then this term is cancel each other, okay, cancel each other. So eventually our value looks like this. And in the end, okay, when we have large n, we have only this part. Right? So it means that if we have more and more observation, the better the fit, which means that if we have large number of x, large number of data, then this term, right, is square of some number. So if we have more and more data, this term is bigger and bigger, right? Bigger and bigger. So if this term is bigger and bigger, then this variance of x hat is getting smaller and smaller. Getting smaller and smaller. This variance is getting smaller and smaller, and then expected value of beta hat is true beta. So if we have a large data, then basically beta hat will converge to beta, because the variance becomes 0. So if variance is 0, it is basically constant, and expected value is same to true value. So if we have enough number of very large data, our OLS estimate will converge to true beta, true estimate, true underlying parameter we are at. So note that, therefore, the more observation, the better the fit, because we have low and low variance. And the more variation, the better the fit, right? The more variation. So if we have large variation, then we have large variation we have large x tilde, right? X tilde square is bigger and bigger, right? So this denominator is become bigger and bigger, right? So therefore, the more variation, the better the fit. And of course, if we have high variation of ui, right, then it becomes larger. So the higher the variance of error term, the worse the fit. So basically, if we want to estimate the as a pricing model, capital asset pricing model. So if we have data, something like this, then our estimation is maybe not accurate. But if we have a large variation in x, if we have large variation in terms of this axis, then we will have more and more accurate line to fit the data. So far, the only assumption we made are there exists expectation, okay, and error term expectation 0, and variation of error term is smaller than infinity, and we assume that covariance, okay, covariance between I and j, in this case it is the same. This one multiplied, actually this one multiplied this one. There is, I think, another error term. So this one multiplied by u square, right? Since I and j are different, if I and j are different, they are identity. Since they are independent, they are all 0. But since if I and j are same, then it basically becomes variance, right? So actually we have to multiply this over here, and covariance 0. So they are the only assumption we made. Okay. Next, testing. Okay. If we are willing to assume that, okay, now, until now, we didn't assume that this error term is, we made any assumption. Okay. Besides mean and variance, we made no assumption. But from now, let's make assumption. Okay. This error term are identically independently distributed, and in addition to that, let's assume that ui is distributed, is drawn from normal distribution. So it is normal distribution from now. This is normal distribution, so and this square hat looks like this. Therefore, it means that since ui is all normal distribution, so therefore beta hat is basically looks like this. The mean of this one is 0 and variance of this one is 0. We already completed over here. Right? So beta hat is basically has normal distribution with beta, mean beta and variance this time. Okay. Now let us do some tests such as beta is equal to beta 0 or beta is different from beta 0. So this is our so it is alternative hypothesis, null hypothesis. So usually we test beta is equal to 0 or not, but here that's more general, such that we want to test whether beta is equal to beta 0 or not. In order to test this, okay, consider test statistic looks like this. So beta hat minus beta null. So on the null hypothesis, on the HO, E should be 0, right? And divide it with standard deviation of beta, right? So given the equation A, right? Given the equation A, okay. Given the equation A, looks like this. So beta hat minus beta null, okay, should be distributed this way, right? Of course, if our null hypothesis H naught is right, right? If that is right, the expected difference between these two should be 0, right? Since beta hat expected value of beta hat is beta, right? True value, and our assumption, our hypothesis is null hypothesis means says that beta is equal to beta 0. So if our null hypothesis is right, the expected value of the difference between beta hat and beta 0 should be 0. Okay. So on the null hypothesis, it looks like this. And since we have this relationship, so this standard deviation, this is variance. So if we divide this one with this one, which means that Z is distributed with standard normal distribution. Right? Z is drawn from standard normal distribution. Now we can check to see if Z is within or outside of the relevant critical values. Critical value. consider some example. Okay. The analysis above require knowing, of course, in this setting, we assume we already know this one, right? Already know this one. However, the analysis above requires knowing this one, and if we don't know, if we know this value, it doesn't create any problem. But in most of the case, we don't know that. Right? If we don't know the variance of the error term, then we have to estimate the error term, beta of error term, and we can estimate error term in this way. Okay. And actually, we will investigate what this one later on, but we can actually estimate this one in this way. And then, if we have this estimation, okay, and by dividing this one, okay, with this one, so it is called basically T distribution with degree of freedom n-2. Okay, degree of freedom n-2. Basically, T distribution is the ratio between normal distribution and chi-square distribution. So anyway, I'll explain that later on. But now, if we know, we know the variance of the U, then we have the standard normal distribution. But if we don't know the variance, we have to estimate it, and we plot the estimated value of this one like this. And this statistic is T distribution. And of course, we have infinite number of n. Right? We have infinite number of n, and this will converge to this one. Right? Because Where is it? Yeah, because of this relationship, so you have enough number of data, then variance of UI hat will converge to anyway the true variance. Okay, so if we have enough number of data, actually we don't have to use T statistic. We can use something G statistic, which is a point in the standard norm. It is Z, which is distributed with standard norm. It shows standard normal distribution. So anyway, the confidence interval. So confidence interval for beta is like I plus minus some t value and standard deviation of beta. We already know standard deviation. And the statistical significance of the beta hat corresponds to the significance of the test with beta equal to 0, right? So, I mean, if we use Z statistic, right, G statistic, and beta hat plus minus 1.96 and standard deviation is 25% in, right? And if we use a G statistic and it is like 2.23, something like that, then it's like 99% error. T distribution is slightly different from G distribution. Anyway, you can find this given the significant interval. Okay, there is a table about T statistic. So basically, you can generate confidence interval, right? Okay. So anyway, if our hypothesized value, which is beta of beta, which is beta 0, if beta 0 is within this interval, we reject the null hypothesis. And we accept the null hypothesis. We cannot reject the null hypothesis. Right? If beta 0 is outside of this confidence interval, right? Then given the assumption, given the assumption about beta, given our hypothesis of the beta, that event is not likely to occur very often, right? So that is a very rare event. So therefore, if beta null is outside of this range, very rare event occurs. It means very rare event occurred given the null hypothesis. Therefore, we reject the null hypothesis. Okay. Any question? You already learned this, right? Any question? You already learned this, right? The 계량금융. Jay, any question?
Actually, I take the statistics class, but I didn't learn the regression.
No, it is not about regression. It is hypothesis
Yeah.
testing, right? So it means just your estimate within the range or not. It is not relevant to calculation. So usually, instead of checking this, actually, we check this number directly. Right? Check number this directly, and if this t value is, absolute value of t is large, if this t value is large, then this value is also large, right? Which means that it is likely to be rejected. The null hypothesis is likely to be rejected. So usually we check the value of the t, whether it is large or small. So if beta naught is within this beta hat t, okay. Oh, okay, minus and cross, and it is rejected, right? So which means that if we subtract beta each side and beta equal right. So if we multiply minus each side, then it is t value, okay? Please specify the t value. So this is minus t. So actually, when this statistic t is between alpha can be, usually alpha is 95% or 99%, right? So if this statistic is within this range, we cannot reject the null hypothesis. If this value is outside of this interval, we will reject the null hypothesis. Actually, I will show you one example. One example is edit. true. So let's say x equals, x is r norm 10. Okay. So r norm is basically, okay. Okay. Oh. Okay, so R norm is R norm. If type R norm, it is basically function such that with mean 0 and standard deviation 1, it generates n random variable from standard normal distribution, right? So like R norm 10, it generates 10 random number from standard normal distribution, and if we set R and mean equals 1 and standard deviation 10, it generates 10 random numbers from mean 1 and the standard deviation 10. Okay, so if we define x as R norm random number from normal distribution like 100, 1000. Okay, 1000 and mean equals 2 and standard deviation like 1. Okay, x looks like this. So we can calculate mean of x, which is close to 2. Right? It is not exact 2 because we have a limited number of error. So we calculate standard deviation of x. It is not exactly 1, but it is reasonably close to 1. Okay, so it generates random number, something like this. So let's generate 100 random numbers, and let us define y equals a alpha plus beta plus x plus u. Okay, and we have defined u. So let's say alpha equals 1, beta equals also 1. Okay, so coefficient is also 1. So we know true coefficient, right? And let's say u is another lambda r norm and 100 and mean 0 and like standard deviation like 0.3, reference 3, right? So we have data looks like this. Okay. Okay, we have data looks like this. So actually in this case, I generated data. Okay, so there is a true relationship. True relationship such that alpha is 1, beta is 1, right? And I know true standard deviation of u, which is 0.3, right? And now, since we have run regression, now let's estimate alpha and beta through regression analysis. And whether regression really generates true alpha and beta. And regression is, okay. It's been a while since I did the regression, so, okay. Let's output 1 equals linear regression such that and want to express y with respect to x, okay. We have only one there. Okay. And let's see output summary. Out 1. If we look at the summary, okay, well, let's take a look at our estimated value. Intercept term. So intercept term is basically alpha, right? Intercept term is 0.95. Okay, so it is reasonably close to 1 in some sense, right? And let's see x. X is 0.99. So it is reasonably close to true value of the 1, right? Do you understand? You understand what I did? Okay, and next, now let us increase the standard deviation into the 10 times. Okay, 10 times. Then this should be less significant, right? So regression and add 1. So we have, yes, slight, still it is significant, but it is actually less accurate. So in this case, R squared is like 0.92. Adjusted R squared, I'll explain about R squared again. So R squared is called goodness of the fit. So high, but now R squared is much lower. Okay, but still we have a significant. So even though standard 10 times, we have significant one, and this is actually not that close to 1, but it is reasonably close to 1 still, right? And we have a t value over here. Okay, t value over here. So in this case, if we do the look at this table, the default alternative hypothesis, default null hypothesis is 0. So assuming our null hypothesis in which alpha beta is 0, this is t value about that. Okay, so t value is about the intercept. First, t value is 4.38. So you already know how to calculate t value, which means that this kind of event is likely to occur with this probability. Okay, since t value is large, so this kind of value is likely to occur. So t value greater than this one, okay, this t is likely to occur with this probability, which is very low, right? So indeed, it means that this kind of t value is a rare event under the assumption that intercept is 0. Therefore, we reject null hypothesis that intercept is 0, and reject null hypothesis that alternative intercept 0, and we can say that intercept alpha is not 0. Okay, and alternatively, we can check whether, okay, we can check whether this estimate is significantly different from 1. In this case, from estimate, we subtract this 1, okay, and then we can divide. Standard error is basically this term. Okay, standard error is basically this term. Okay, standard error is basically this term. Standard error is like this. So I forgot coefficient. Okay, coefficient minus first element is this one, so minus 1. Okay, looks like this, and then let's see, SE, no, standard error. I don't know how can be the standard error. LM regression, and then okay, argument, formula, data set, offset, details, value, residuals, term, x value, offset, model, array action, coefficient, residuals, period values, like it doesn't generate. Coefficient, why? Normally out one is coefficient, standard error. Anyway, okay, and then copy and paste this standard error. So minus 1, and let's divide this one with standard error, which is 0.3206, and this intercept, this value is like 1.26, and I have to check cumulative distribution of this one, but I'm pretty sure that this value is within the range, within the range of inner one. So I think in this case we cannot reject hypothesis that this estimated coefficient is different from 1. Okay. So CDF, let's check it. CDF R cumulative distribution function T distribution. Okay. R page probability student T distribution. Okay. T, okay, T is normal distribution and inverse cumulative T by normal. Okay, T distribution, dt, y. Okay, PT, okay, PT is the cumulative probability density function. So what we can do is PT. Okay, let's go and PT, and degree of freedom is we have how many data we have? We have like 100 data. 100 data. So degree of freedom is 100 minus 2. So this is like 0.89. Okay, so our estimated T statistic under the hypothesis that our estimated constant freedom is 1. Okay, which means that our T statistic is T distribution. So our T statistic around here, which is beta 10 minus beta 0, which is 1 in our hypothesis. 1 minus standard error is around here. So this area is around 90%. So this area is about 10%, right? So if we want to test on the 99% interval, then actually this area should be 0.5%, and this is much inside of this range, right? So if we use 99% interval, we cannot reject this hypothesis. In addition to that, since this area is 10%, so even if we use 95% interval, in each case, the area of this part should be 2.5%, and this is greater than 2.5%, which is 10%. So still we cannot reject this null hypothesis. We cannot reject the hypothesis that alpha is close to 1, alpha is 1. Right? Again, we can reject the hypothesis that alpha is 0, but we cannot reject the hypothesis that alpha is 1. Like this. PT, right? PT. I didn't know that PT. Okay. Actually, degree of freedom. Okay, same. I have to do myself. Any questions? So anyway, let's do more exercise. So coefficient. Okay, let's check the coefficient. Is summary out 1 and then coefficient looks like this. So to get the standard error, what I can do is interesting, that's standard error. Okay, anyway, this is coefficient. So if we want to see only this estimate, what we have to do is plot this one. So we will get the first column. Okay, and this is regression analysis using the built-in function of the R, and instead we can use the formula, okay, directly this one, okay. Right. Now let us try the formula this one, right? Beta should be the ratio, estimate of beta should be ratio between covariance of xy and then variance of x, right? So let's try this one. So let's say beta hat, then p hat. Let's define p hat as the covariance of x and y, and divided by variance of y, right? And the answer is p hat is 0. Why it is different from this one? That's interesting. What? Oh, sorry. It should be x, right? It should be x, right? So right, exactly same. So when we use this formula, right? Right? This one, okay, where is better? This formula, okay. This is exact, this value is exactly same to the coefficient for this one, right? And let's calculate alpha hat. A hat should be, okay, mean y minus b hat, okay, this is b hat, this one, and multiplied by mean x, right? If we calculate this, a hat is 1.40, which is exactly same to this one. Okay, this is what I just did this analysis. And then about the variance, okay. Okay, hold on, and I forgot how to regression, okay. Anyway, let me close this one. And then what else we can do? Okay, let's try this one now. Okay, so in our estimated beta, okay, beta should be okay. Our estimated, okay. Now in our program, we know the true standard deviation of u, which is 3, right? By this is 3, and we let us estimate this one, okay, and whether we have a similar value or not. Okay, so okay, let's go this one, and then so we have a hat and b hat. So what we can do is y minus, let's define y hat as, okay, a hat plus b hat multiplied by x, okay. So x is our data and a hat, b hat is our estimate. So y hat is actually our estimated y, right? And y minus y hat, which is the error term, right? And if we calculate variance of this one, y minus y hat, which is variance of this one, it is about 11, right? 11. So since our standard deviation is 3, so variance, our original true variance is 9, but it's slightly larger than that, right? But if we multiply this one and by using formula of this one, so 100, we have 100 data, right? Our data size is 100, so 100 minus 1 and divided by 100, and then the size is slightly smaller, but actually not that smaller, okay. So anyway, the true variance is 9, right? This is our true standard deviation. So our variation is actually slightly larger than that. But if we increase the data size over there, I'm pretty sure, or we can have even closer data. So let's check. Let's increase the number of data. So let's make T data size, and T is 1,000. Actually 10,000, very large data set. That's t. Okay. So source rake R. We have large data. So even though we have large data, still we have very it's very quick, right? So summary out 1 and coefficient actually the summary. Okay, so yes, we have very strong. It is very close to 1. Right. So next, given this estimate, what we can do is let's define y hat as L1 coefficient. Okay, 1, 2, so it is 1. Okay, now I think it is better. Plus actually, let's take alternative way. Let's define this is a hat. Now again, a hat is the first element of the coefficient. Okay, b hat is out 1 to the second element. Okay, so our y hat is a hat plus b hat multiplied by x, right? So it is our estimate. So now check the error value. So actually SD, standard deviation of y minus y hat, which is now 3.14, which is a lot now closer to the true standard deviation 3. Right? So we have, since we have larger data, so we have more accurate estimate of the true variance. And of course, if we have infinite number of data, we will get eventually the exact 3. It is very true. Standard deviation. Any question? It's pretty easy, right? I mean, even in this regression, compared with the previous 100 data, since we have now 10,000 data, right? With more and more accurate numbers, so these estimates are very close to 1. Then you can see very close to 1. And this t value is very huge. Standard is very small. Very small. So, very small. So, they are extremely significant. This kind of a t value is likely to occur with almost zero probability. Right? Of course, again, this t value is a t value under the assumption that null hypothesis is right, and the null hypothesis, in default null hypothesis, is that intercept is 0 and coefficient for x is 0. So this is the univariate regression, and for your homework, you have to multivariate regression. So in that case, okay, let's say there should be x1. Okay, so in your case, first is market premium. Okay, in Pharma French 3-factor model, market premium and SML, small minus large. Let's say it is another R norm T. For fun, let's plus 1 here, and H minus, actually small minus big, high minus low. Okay, let's say it is R norm T plus 0 for fun, and then let's say alpha is 1 and beta is like C 1, 2, 3. It's 2 extreme. 0.1, 0.2, 0.3. Okay, better looks like this. So U is T, let's make it simple. Let's say write just 1. Okay, 4. And our model means that y is beta 1 plus element. Let's mark it. 2 multiplied by small minus b plus beta three, so the element high minus low and plus u. Okay, so this is our data, and in our regression what we have to do is, okay, regress y on market, okay, and small minus big and high minus low. Okay, and let's run the regression. Source oh, sorry, actually I have to plus over here, sorry, plus, okay, R, and let's say summary out 1, okay, summary out 1, then we have this relationship, so we have very accurate estimation. So our true alpha is 1 and it is close to 1. Of course, if we believe gamma function 3 factor model really, then this intersection should be 0. If this is the case, then something will be gamma function 3 factor model. But anyway, it is practical. It is close to 1, which is true value alpha. And our coefficient, our market coefficients, side factor, and value factor, we assume it is 0.1 and it is close to 0.1, and it is 0.19, which is again close to 0.2, and this is 0.3039, which is again close to 1.3, right? So okay, we have reasonably good estimation. And t values are all extremely large in reality. In real life, t value never rise this way. So within your standard error, which is 1.013, which is again close to standard error 1. Visual error we have very best way. So R squared is about 12%. So our data explains about 12% of intel variation of the Y. So this R squared means that basically our data, constant term and the market, SMB, HML jointly explain about 12% of entire variation of the Y. And more accurately speaking, if we use adjusted R squared, still it is close to 12%. Variation. Any question? Anyway, let's call it a day, and good luck to your homework, and see you next week.